can cause a chain reaction that can happen in a heart, well, less than a heartbeat, in fractions of a second. And so large amounts of energy are released. And that energy, if controlled, can be used to heat water, which that heated water then can drive turbines and generate electricity. And that's basically what we do with nuclear power. We split radioactive material, and of course uranium then becomes a very valuable product, commodity. And it's like the fossil fuels. It's going to run out someday. It's going to reach the point we can't find anymore, but at least not affordably. Now, fusion, here's an uncontrolled fusion reaction. What do we call that? We call this a hydrogen bomb. Well, that's a fission reaction. I'm sorry, that's called an atomic bomb. I'm getting ahead of myself. This is the kind like we dropped on Hiroshima and Nagasaki. Einstein and a few of his buddies, Oppenheimer, and a few of those guys in the Manhattan Project theorized that it would work like this. But when those pilots were flying over Japan, they didn't have any idea. They just knew this was a super bomb. They didn't actually know what they were doing. And this is uncontrolled fission. If it's done in a reactor, it's controlled. But a bomb is just an uncontrolled fission. We let the process of chain reaction happen quickly and in large amounts, and we create an atomic bomb, which did a lot of damage. But what we didn't realize we were doing is changing the genetics of the people that lived in and around there that survived those bombs. And that's later on, the pilots, many of them committed suicide, died unnatural deaths, had severe mental problems to the rest of their lives when they realized what they had done.
Is it something that the atomic bomb gives off, like radio?
It gives up radiation, and you can be poisoned. It gets in the water, it gets in the air supply, and any kind of radiation, even the radium in your glowing watch dial is putting out radiation. And it can be a little bit hazardous, but there's not enough in your watch dial to do a lot of damage. But it's like everything else. We don't talk about whether something actually does damage or not. We talk about an acceptable level. Okay. It's like the rodent hair in the payday candy bars. There's an acceptable level of rodent hair in payday candy bars. And you don't like to think there's any rodent hair in payday candy bars. But anytime you have peanuts, you're going to have rodents. They love them. Not just monkeys. And so a fission reactor on a large scale, basically, you can control the amount of fuel that you add at one time of the radioactive material with movable rods. This used to be done manually. Now it's done with computers. And the heat generated from the fission process is used to heat water and create electricity to drive the turbine. So when everything's working hunky-dory, this is all nice. Now, occasionally, one of these things will overheat and blow up. And we have a problem like we had, we'll talk about, probably not today. But basically, that's what happens. We have a reactor, produces heat exchanger, translates that heat into steam, or water, steam. It heats the water, creates steam, drives a turbine, which turns a generator, which produces electricity. That is really the sole use of nuclear fission. Even your nuclear submarines are making steam to drive a turbine to make electricity to turn the propellers. That's the way they are. Now, I wanted to get this, and then we'll stop. There are pros and cons of using nuclear energy as a viable source, the fission reaction in reactors, versus burning of fossil fuels. We're going to use coal as an example. To me, this is an interesting set of slides. Now, if we look at the impact of land use, to make a certain amount of energy, it takes 17,000 acres to be equivalent to build the plant and so forth, as opposed to 1,900 acres if you're making a nuclear power plant. So as you can see, there's about an 8-fold reduction in the amount of land it takes for the facility. So that's a plus. Anytime you can do this, create the same amount of energy for less acreage, then that's a good thing. Because land is a commodity that's running out too. They're starting to make different rules in our little cemetery back home, where my tombstone and my wife's tombstone are now sitting prominently among her family. You can't bury 3 people in a grave. In fact, you can't even bury 2. You could put a buried person and a crematory urn in the same grave. They got all these rules now because they're running out of space. We're going to be cremated, but they don't have cremation spots that would be a third or half the size. So we have to take up full, if we've been thinking we'd have been buried in the same plot, they'll let you do up to 3 crematory urns in one plot. All right, daily fuel requirement. Well, it takes 9,000 tons of coal a day, about 18,000 pounds, to make the equivalent of 6.5 pounds it takes of nuclear fuel. 18,000 pounds of coal and 6.5 pounds of nuclear fuel will make the same amount of energy. So you can see there's a we're not using, although uranium is a finite product, it's going to run out too someday. We don't use nearly as much of it to create the same energy. Air pollution. Coal puts out moderate to severe, depending on how advanced the coal burning facility is. Some of them just belch raw smoke into the atmosphere. Others have collectors, electrostatic collectors that pull the soot out, and others even have stuff that removes the carbon dioxide and some of the other gaseous components out and recycles them into something else. But as you go up in complexity, of course, the cost of it goes up. And different countries, different parts of our country have a relatively different ability to do that, come up with these high-tech things. It's like CSI. That technology exists, but not very many CSI facilities have all that technology. Anyway, it's pretty low in a nuclear power plant because there is no burning per se. There's just the breakdown. We can have an occasional neutron gets spit out randomly, but that's not like a lot of coal soot and so forth as you burn it. Radioactive emissions. Well, here's maybe a con. Marie Curie was a scientist that studied radiation, and so they named the unit of radiation after her. She was a French physicist, and so just using that as a reference, not caring about the technical physics definition for it. 1 unit, but a nuclear plant may put out 28,000 units of, or current curies of radiation. So coal is not nearly as radioactive in its emissions as a nuclear plant is. There is uranium bits in coal, so when you burn coal, you are releasing some radioactive materials, but not anything like during a nuclear fission reaction. And the risk from catastrophic accidents. With coal, it's short term. In other words, it doesn't last very long. You have a blow up, you put the fire out, there's some smoke pollution, and the risk is pretty localized right around the plant. But in a nuclear facility, the extent can go all over large